hydroelectric plant works. So here's a diagram of a hydroelectric plant, but it's more commonly known as a dam. Shown on the left side of the diagram, you have what is called a reservoir, which is another name for lake. Now the water flows through the intake, which is the gate-like structure that helps control the flow of water. Furthermore, the water begins to flow through the penstock. Depending on the amount of drop in elevation will determine how much power will be produced. The reason is that gravity will be pulling the water down, resulting in the water flowing faster through the penstock, which will allow more water to go through the intake and produce more power. At the end of the penstock, you'll find a turbine. At the bottom of the turbine are propellers. Now when water flows through these propellers, they begin to spin. And when the propellers are spinning, the rotor, which is located at the top of the turbine, begins to spin too. This will produce power through the generator, which is located above the turbine. And these are both connected through a shaft. Now the generator is located in a powerhouse which houses a bunch of other generators. Power lines are connected directly to the generator to give direct feeds to homes and businesses. After the water leaves the turbine, it'll flow back into the river. This will be known as a renewable source.
Hydroelectric plants are safe for the environment. Since hydroelectric plants do not burn fossil fuels, they do not directly produce carbon dioxide. Hydroelectricity eliminates the fluid gas.
Electricity is a form of energy resulting from existence of charged particles such as electrons or protons, either statically as an accumulation of charge or dynamically as a current.
The way electricity and magnetism are related are by a magnetic field can be used to produce electricity. In fact, magnetism and electricity are really two permanently related parts of one fundamental force called electromagnetism. Every time there is a change in a magnetic field, an electric field is produced. Every time there is a change in an electric field, a magnetic field is produced. We can use this relationship to produce electricity. The pressure that pushes electrons in a circuit is called voltage. Voltage is a measure of the strength of the current in a circuit and is measured in volts. The way voltage works is it sends out electrons with sufficient force to flow around the circuit and light up the bulb. The water razor is equivalent to voltage. Then current is the number of electrons following past a fixed point in a certain amount of time. The way it works is it's measured by the rate electrons pass a given point in an electric circuit. A higher number of electrons mean a higher level of current. Resistance is a property that slows the flow of electrons down. The way it works is the circuit with the high resistance will allow less charge to flow, meaning the circuit with higher resistance has less current flowing through it. Ohm's laws is the current through a conductor between 2 points is directly proportional to the potential difference across 2 points, introducing the constant of proportionately the resistance. One arrives at the usual mathematical equation that describes this relationship. The way it works is the formulas of Ohm's laws are V equals I times R, or the predator of the current is I equals V divided by R, or R equals V divided by C. Electric power is the rate at which electric energy is transferred by an electric circuit. Electric power is usually produced by electric generators, but can also be supplied by sources such as electric batteries. And the power formula is P equals V times I, the P equals the watts, the I equals the amps, and the V equals the volts.
Electromagnetic induction. Prepare a circular coil out of copper wire. Connect the two ends of this coil to the two terminals of a sensitive galvanometer with a scale having 0 at the center. This closed circuit is shown in the diagram. Note that this circuit contains no source of electricity and the galvanometer shows 0 reading initially. Take a bar magnet NS and move it swiftly towards the coil with its north pole facing the coil. You will observe a deflection in the galvanometer when the magnet is moving. The deflection indicates that current is set up in the coil. Now, move the magnet away from the coil. The galvanometer shows again a deflection, but in the opposite direction. This means current is set up in the opposite direction. If you hold the magnet with its south pole facing the coil and repeat the above steps, the deflections are again observed, but are reversed. Similarly, motion of the coil itself also produces deflections in the galvanometer when the magnet is kept stationary. Do you observe any deflection when you just hold the magnet stationary near the coil at rest? No. A relative motion of a magnet and a coil induces the current in the coil. The current produced by a relative motion of the coil or the magnet is called an induced current and is said to be set up by an induced electromotive force, EMF. The production of an induced EMF in a coil in a closed circuit by a relative motion of a magnet and its coil is called the phenomenon of electromagnetic induction.
A generator engine converts diesel fuel to mechanical energy that rotates the crankshaft. As combustion occurs in each cylinder, energy transmits to the engine crankshaft, which generates mechanical power for the alternator. An alternator converts mechanical power into electrical energy in a process called magnetic induction. Magnetic induction occurs when a conductive material such as a copper wire passes through a magnetic field and voltage is produced. If the wire is connected in a complete circuit, the power can be transmitted. Alternators include two primary parts, a stator and a rotor. The stator contains copper coils wound into the alternator's outer casing. The rotor also has wire coils wrapped around an iron core, but unlike the stator, it is attached to the engine crankshaft so it rotates with the engine. When voltage passes through the rotor coils, it creates an electromagnetic field. As the rotor spins, its magnetic field cuts across the stator's conductive wire and generates voltage. Because the magnetic field builds and subsides, voltage fluctuates between positive and negative peaks, which is known as alternating current. The stronger the field, the higher the peaks. Ideally, voltage levels should be consistent so that constant power is provided when under load. To do so, an automatic voltage regulator, or AVR, adjusts the magnetic fields as needed. During heavy power demands, voltage decreases, causing the AVR to increase the magnetic field. Conversely, when power demands are low, the AVR tempers the field. Doosan mobile generators also include alternators with 6 coils wound into the stator. This provides 3 voltage sources or phases. Because each phase combines 2 coils of wire, the sources can be connected in series for high voltage applications or in parallel for low voltage needs. To simplify wire connections, Doosan mobile generators have a convenient selector switch. When an operator selects the desired voltage, the switch adjusts the connections.
A power supply is a device that supplies electric energy to an electrical load. The function of a power supply is to convert one form of electrical energy to another. And then AC and DC, the difference is the direction of flow. Alternating current, which is AC, changes directions periodically and the voltage level reverses along with the current. Direct current, DC. It stays constant voltage or current that it flows in one direction, but the voltage and current may vary over time only as long as the direction of flow does not change.